Okay, hello everyone. So I'm calling this talk Faking It in AI because I was word playing around with the phrases fake it till you make it and of course faking it in AI. So so my thinking there was fake it till you make it. That reflects a philosophy I'm interested in, a philosophy in engineering innovation that works for me anyway. This idea of imitating competence to gain competence, that sort of thing. I think it's a very valuable mindset that good engineers often embrace, probably maybe subconsciously or covertly, because professionally engineers often need to project quite a conservative sort of, yep, that bridge isn't going anywhere sort of, professionalism and mastery of their art, right? But of course, engineering is all about risk taking. So when it comes to engineering innovation, especially in an area like machine learning or AI, where the half-life of knowledge is something like probably about 12 months or so, you're always chasing competency or flirting with incompetency. So my thoughts on that are just to get comfortable with that. That's where we are. That's the world we live in now. So, embrace that. It makes things exciting. And also the upside, of course, is that there's always an opportunity to go from, to break into a new area and to go from zero knowledge to mixing it up with the experts in a pretty short space of time. So on that note, let's move to the faking it in AI bit. So as you probably realize, I'm going to talk about my own team's journey starting out faking it in AI, imitating competency, to gain competency. And what makes this interesting is, I suppose, as well, is that a lot of our research ultimately really got into faking it in AI, literally fakes, deep fakes in AI, and how we use that to solve engineering problems. So in 2018, so it's when I started really making this little pivot, or quite significant pivot, into kind of deep learning sort of technologies. Um, my engineering team and myself, we would do a lot of work in machine learning anyway, but in our area, our chosen area of brain-computer interfaces. Um, and there, the machine learning, it was, I don't say it was easy, because we're trying to listen, measure signals from somebody's brain and figure out what they're thinking, or figure out if they're might move their left hand or their right hand, for example. But we'd go heavy on the signal processing, or taking the signals from their brain and mathematically being very clever about how we would transform it into features that would be very discriminative, very clear about what they're saying in the brain. And then our machine learning algorithm didn't have to do very much work. It would just needs to see if one or two signals are going above a threshold. It's nearly be just a threshold detection, right? So we put all the work traditionally into the feature processing, or the feature engineering, and left the machine learning pretty light, well, relatively speaking. But we could do good things like this. For example, this nice little project we had, or thing that we developed, a nice piece of innovation, where this is a real-time attention monitor. So we're actually working with little wearable headsets here, some of the team that I was working with, and we were measuring brain signals. And in this game that we came up with, we were processing the brain signal to focus in on an aspect of your cognition or your mental state related to paying attention, right? Which maybe, hopefully, people are still doing during this talk. Um, I mentioned that because that idea of paying attention and monitoring a person's attention via brain signals is a nice application of machine learning, and something that we're currently doing to look at driverless cars, or blended autonomous vehicles, or blended control of autonomous vehicles, such as driverless cars, where there might be some remote supervision by a fleet, somebody managing this fleet of cars and monitoring their attention, and we call that neuroergonomics, is a cool thing to do, right? So that's one of the applications we're doing of brain-computer interfacing. But my point here is that our machine learning, even though this is a sophisticated problem, the machine learning that we used wasn't that sophisticated. Signal processing was, right? So anyway, when in about 2018, wanted to see what we could do with deep learning techniques and see if there's anything interesting we could turn our hand to. So kicking out from brain-computer interfaces, I thought I wanted to get into, you know, I was thinking, where do we fall short in some of the engineering things we look at? And it's usually in the real world when we're trying to measure what people are thinking and doing in the real world, which is a noisy place, right? A very noisy, messy place. And the traditional signal processing approaches and engineering approaches we take to trying to measure what people are doing, they kind of fall flat in the presence of lots of noise and lots of kind of sources of error, if you like. So we started with something simple. We started with wearables. Now, not brain computer interfaces or measuring, something sophisticated like that, just wearables like a Fitbit, right? Because wearables are everywhere. And because they're everywhere, we can get lots of data from them. If there's one thing I didn't know about deep learning at the start, that generally they needed lots of data. Well, not generally, they did need lots of data. They do need lots of data. So here was our first problem that we kind of looked at that made us think about where deep learning might be able to help us. Let's look at a Fitbit, right? Let's look at the heart rate signal that might be measured at the back of your Fitbit. It's a little pulsatile signal, like you can see on the screen here. And by counting those pulses in a unit time, you can figure out heart rate, right? That's your heart pulsing away there, essentially. Well, the blood vessels um, associated with the heartbeat. So now, what's interesting about that with a Fitbit, when somebody's, the signal looks very easy there, it looks nice and clear, but when somebody's maybe walking, right, that sensor is bouncing off their hand. And so you get lots of artifact, it gets messy. It's a classic example of this messy real world situation I was just referring to there. Look, and then it gets even worse when you're doing more strenuous things. Here's somebody running here on the top right. Somebody's running, the sensor's really bouncing off, and it's very hard to measure heart rate in that situation. Even though I know your Fitbit, it does purport to tell you what your heart rate is when you're running and walking, but it's got its work cut out for it, right? But when we looked at this sort of challenge, classical machine learning on classical signal processing kind of fails. But it's interesting. If I showed you some other this bottom right hand corner here, this is more data from that Fitbit. If I asked you just by visually looking at it, do you think this was when somebody was resting, with no noise on the signal, or walking or running? You might, from looking at it, even though I know it's probably not streaming very smoothly here, you might say that looks a bit like running, doesn't it? That looks similar sort of characteristics. So how are you doing that? How are you making that discrimination, right? You're eyeballing it, right? So we thought, wow, if you can eyeball it like that, is that not what these deep neural networks are getting good at? These convolutional neural networks, this sort of AI that we hear about? And sure enough, it is, right? We looked at Google's Inception, right? Google's Inception is a deep neural network, a convolutional neural network that was really good at working with this kind of classic competition data set, which contains millions and millions of images of all sorts of things. And, cats and dogs and, cars and airplanes and ham sandwiches or whatever, right? Lots of these sort of images. And it was incredibly good at being able to distinguish these things. And when we read about that, we said, that's really cool. I wonder, could we teach it to look at those plots and learn, those heart rate signals, and figure out that this is somebody's Fitbit data when they're walking, and this is when they're running, and this is when they're on their bike or something, right? That'd be cool, right? So rather than getting upset about the disruption in that wearable signal, we use that disruption to figure out what people are doing and to get a human activity recognition with that Fitbit. So what we did was we took this quite very complicated neural network, right? For us it was, for sure, right? It's got many, many layers and so many neurons, and training it must be a pain in the neck. But we learned about transfer learning. That's where you teach an old network like this Google's Inception v3, and you just train it a little bit, a particular part of the network, on your data. And so it retains all the knowledge it had on learning cats from dogs, from ham sandwiches, from airplanes, but could then maybe learn whatever idiosyncratic thing you wanted it to teach, that you wanted to learn, such as these images, these time series, these signals. So that's exactly what we did. So we trained the last layer, or the second last layer of that network, and we showed it lots of these Fitbit data signals. And sure enough, it was able to detect whether somebody was walking, running, cycling, or just going for a gentle stroll or cycle with like world-leading accuracy for that particular type of problem. I think it was 92% accuracy we got on that, while the previous result we used in classical machine learning was something like 60%. So we totally faked that. We didn't really. We just had a clever idea of hacking it, if you like, of just doing transfer learning, and that was super. And then I got us thinking, yeah, we're really faking it here. We might make it. And then we saw what else we could do. So check out this. This is an interesting little challenge about it's related to fakeness.
In tonight's Tech Minute, millions of Americans have Fitbits and pedometers in order to track their physical activity.
But as CBS 4's Gilma Abelos reports, some people have figured out how to earn steps without ever taking one.
This man isn't doing laundry. He's asked us not to show his face because of what he is doing with his company-issued step tracker.
Put the Fitbit in a sock, hour and a half on no heat setting in the dryer, 11,000 steps. Thank you.
He's earning 11,000 steps without moving. As is the case for many employees, his pedometer is linked to company insurance incentives that can lower his payments.
You are now more involved in, well, how much is this bill? How many steps?
Companies benefit from a healthy workforce, and many are rewarding workers with freebies for getting fit. But there's also a growing movement online to cheat the system.
We're starting with 34.
So I don't have time to play all this, right? But look, people are faking it, really faking it with their Fitbits. And so we said, wow, that's interesting. Can we detect that? Can we figure out if you've taken your Fitbit and you've thrown it in a sock in the dryer, or you've given it to somebody else who likes going for runs every day, and they're running around with about 10 Fitbits on their arms, right? And sure enough, that same trick, our little, Google Inception V3, we taught it that. And sure enough, it was able to tell the very subtle differences between different people using their Fitbits. So again, we were able to detect fakes, people faking their the phonies with their Fitbit swapping. So that was a fun thing to do, and that kind of unramped us onto deep learning, because it started with transfer learning and deep learning. I know there's probably a lot here to take in, but transfer learning is kind of a good way to start with deep learning. And there's lots of frameworks like Keras and PyTorch to allow you to kind of very quickly try out some ideas. So after that, we said, faking things really interesting. Let's see where we can go with this. So then we thought more about faking it, and then we started thinking about deep fakes. And here's how that appeared. We're looking at this problem where we're looking at brain signals from newborn babies, and there's algorithms that would look at the brain signals, and there we're seeing brain signals on the screen here, and these algorithms can be used for detecting seizures and things like that. But often there's data missing. Data pops off, the electrode pops off, the data's missing, it messes up everything. So that's a problem. What do you do there? So we gave ourselves that challenge, and we said, well, what can we do? Well, around that time, we became aware of deepfakes started becoming a thing. Like all these images you see on the screen here, that dog, that scene, that kind of a butterfly thing, and that burger, they're all fake, right? This is the deepfake stuff that we're beginning to see. So we said, well, could we do something similar? And again, we started very gently by teaching it pictures, transfer learning on a well-known generative adversarial network, right, which is one of the technologies that up until very recently was a leading technology for fakes. And here were some ECG signals. So it's not brain signals, it's heart signals. So it's easier to distinguish. So we use the same concept, right? So for example, if I ask you if you to draw with a marker, what signal is missing there, you probably replicate what you see to the left and right of it, the ECG sort of waveform, the heart waveform. And indeed, we, by using transfer learning on a well-known GAN, was able to do something similar. And that was our first sort of really big result. So a really interesting result, because that's in time series, right? They're in signals from the body. So we were faking physiological signals from the body. And then after that, we got particularly good at it, right? And so now we come up with our own architectures rather than borrowing or transfer learning over somebody else's well-trained network. We developed our own. And this is my work of one of my PhD students, Owen Brophy, produce a really good result, kind of a leading result. So we're mixing it with the experts now on multi-channel time series from the body. So the signals are all coupled. So you can't just fake one of them in isolation. You have to fake them all together, and together they have to be plausible. So this is some work he's done recently. And so I guess it's a kind of a whistle-stop tour there, but that's sort of our journey in a real nutshell, where we started knowing not very much, started on-ramping through existing deep deep learning technologies and hacking them to make them work for us, till we built up some confidence. And that once we built up some confidence and some knowledge, we were able then to turn that around and be able to develop really new technologies ourselves and actually finally making it. So maybe we'll have a chat about that.